Pluto is a far-off and stealthy, more humble planet that was once a piece of our close planetary gathering. However, recent declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning discovery. They suggested that this icy world is on a potential impact course with Neptune. But how could this actually happen, and what might be the consequences of such a massive event? Are we witnessing a fascinating cosmic phenomenon, or is there more to this approaching calamity? Join us as we explore the potential consequences of a Pluto-Neptune collision. Pluto, a former planet relegated to the status of a dwarf planet, remains a subject of interest and study in the astronomical community. According to recent calculations by leading experts, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising alarms about a possible collision between these two planets, which could pose a significant risk to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. Since its discovery in 1930, Pluto has not yet completed one full revolution. But the intrigue doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, differing greatly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more fascinating is its inclination, tilted at 17 degrees to the ecliptic plane. The way Pluto travels is far more extreme compared to other planets. This inclination and eccentricity add layers of complexity to its orbital dynamics. One of the most interesting aspects of Pluto's orbit is its crossing point with Neptune's. For about 20 years in each orbit, Pluto actually gets closer to the Sun than Neptune does, defying what we might expect from their positions in the solar system. This leads to a natural question. Why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Early astronomers tried to understand its unique path. Unlike other planets, whose orbits are relatively close to the ecliptic plane, Pluto's orbit stands out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit does cross Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricacies of celestial mechanics. The three-body problem in space involves determining how three objects, such as Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict their future positions based on where they started and how they interact gravitationally. In Pluto's case, this problem demonstrates how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex manner. Terms like asynchronous libration, orbital precession, and the VZK oscillation are key to understanding this puzzle. Asynchronous libration, in the case of Pluto and Neptune, means that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from overlapping. Orbital precession refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, providing an additional layer of protection from potential collisions. Another important factor is the VZK oscillation, named after three researchers, Vladimir Zhitkoff and Kai, who studied how objects move in space. This oscillation explains how Pluto, Neptune, and the Sun interact gravitationally. Despite Pluto's seemingly erratic path, this oscillation helps maintain its motion over long periods. The VZK oscillation shows that while space may appear chaotic, there are patterns and rules that ensure stability. These factors keep Pluto's orbit stable and prevent it from colliding with Neptune or veering off course. This three-body problem is essential for understanding how these orbits change due to gravitational pulls. Studying this helps scientists learn more about Pluto, our solar system, and even distant worlds and stars. Mathematical simulations in the late 1980s revealed that, despite its stable properties, Pluto's orbit is chaotic. Minor deviations in initial conditions can lead to significant differences over thousands of years. However, these rare properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively mitigating disturbances. Later automated studies helped us understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps stabilize Pluto's orbit. However, Neptune is not the only player. Jupiter's gravity also plays a significant role in stabilizing Pluto's orbit, with Saturn contributing as well. These studies show that Jupiter's immense gravity is strong enough to keep Pluto on a steady path for a very long time, even millions of years. It seems that Neptune, Jupiter, and Saturn work together to ensure Pluto continues to move safely through space without encountering trouble. These phenomena are fundamental to maintaining order and stability in the solar system. Without these mechanisms, the solar system as we know it would be far more chaotic. Bodies like Pluto could collide with others or be ejected from their stable orbits, triggering a chain reaction with other celestial bodies. For Pluto, particularly with discussions about its potential collision with Neptune in the future, understanding its orbit is critical. This provides a clearer picture of the dynamic nature of the solar system. The case of Pluto demonstrates how even the most seemingly unstable orbits can achieve balance through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often leads us to confront the strange nature of celestial bodies, and Pluto's orbit is a perfect representation of this eccentricity. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is clearly illustrated in Pluto's case. Even slight changes in the dwarf planet's position or speed can significantly alter its long-term orbit. Using automated simulations has been immensely helpful for researchers in understanding how Pluto moves through space. These simulations use complex mathematics to model how Pluto and other space objects like Neptune influence each other. By tweaking small details in the simulations, space scientists can see how even tiny changes might impact Pluto's trajectory over time. These simulations have revealed surprising insights about Pluto's long-term stability. Despite its erratic orbit, the gravitational influences of the giant planets help keep it in check. For instance, Pluto's resonance with Neptune plays a pivotal role in preventing a catastrophic collision. This resonance ensures that, despite their orbital crossing points, the two bodies are never in the same place at the same time. Further analysis shows that Jupiter's immense gravitational pull adds an additional layer of stability to Pluto's path. Even as Pluto's orbit shifts over millennia, the combined influence of Neptune, Jupiter, and Saturn keeps it from drifting too far off course. This interconnected balance highlights the delicate dance of celestial mechanics in the solar system. Without these stabilizing factors, the solar system might look very different today. Collisions between planets or ejections of celestial bodies could have disrupted the delicate balance, altering the evolution of the solar system. The study of Pluto's orbit serves as a reminder of the intricate harmony that governs the movements of celestial objects. Looking to the future, astrophysicists continue to explore how Pluto's orbit might evolve over millions of years. Automated simulations and advanced mathematical models are helping researchers predict potential scenarios, from minor orbital changes to rare but possible interactions with other celestial bodies. Despite its relegation to dwarf planet status, Pluto remains an object of fascination. Its complex orbit, unique relationship with Neptune, and interaction with the gravitational forces of other planets offer invaluable insights into the mechanics of our solar system. As our understanding of the universe deepens, Pluto serves as a symbol of the dynamic and interconnected nature of celestial bodies. The story of this icy world is far from over, and future discoveries may reveal even more about its role in the ever-evolving narrative of the cosmos. The position of Pluto can immensely affect where it ends up in the last part of the 1980s. These recreations showed something fascinating about Pluto's orbit. Despite the fact that it has components like non-concurrent libration and orbital precession to keep it stable, its orbit can still be irregular and capricious. If you start with only a small difference in where Pluto is or how fast it's moving, its orbit could end up looking completely different after a few years. Yet, even with this chaos, Pluto's orbit remains stable over extremely long periods, like billions of years. This demonstrates that Pluto's journey around the Sun has a kind of order to it, even though it initially seems chaotic. Predicting celestial events, especially when they involve volatile orbits like Pluto's, is a tremendous challenge. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While mathematical models provide powerful tools for understanding and forecasting the future paths of celestial bodies, they also highlight the limitations of our predictive abilities. These models heavily rely on the accuracy of initial conditions, and any small error or distortion can lead to vastly different outcomes, making precise forecasts a daunting task. The turbulent nature of planetary orbits like Pluto's reminds us of the ever-changing, dynamic nature of the universe. While we've made significant strides in understanding space, Pluto's case reminds us of how limited our knowledge of the universe still is. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can significantly influence the stability and direction of other bodies within the system. So why are leading astrophysicists recently raising concerns about a possible collision between Pluto and Neptune? Despite all these complex forces working to prevent such an event, Neil deGrasse Tyson, a prominent astrophysicist and significant promoter of cosmology, offers a unique perspective on the mysteries of our solar system, particularly the intriguing case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, offers thoughtful analysis on the evolving nature of celestial mechanics and the public fascination with the overlooked realms of space. Tyson's stance on Pluto's reclassification is rooted in the ever-growing knowledge of our solar system. He views the reclassification not as a diminishment but rather as a significant adjustment to our expanding understanding of the numerous bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits like Pluto's as a reminder of how much there is still to discover in space. The curiosity surrounding these questions keeps the exploration of space so exciting. However, despite Tyson's optimism, his thoughts on Pluto's potential collision with Neptune paint a different picture. His concerns about the future of Pluto's orbit suggest that we may still have many mysteries to uncover. Will Pluto collide with Neptune, or is this just another moment of confusion in the ever-changing universe? Only time and further research will tell. For now, we are left with a deeper curiosity about how little we truly know about our own solar system. The possibility of a Pluto-Neptune collision raises yet another question about the mysterious and captivating universe in which we exist. The potential for such an event challenges conventional understanding of planetary stability. The idea that two celestial bodies with such vastly different characteristics could collide is both unsettling and fascinating, especially considering the current relative stability of their orbits. Given that Pluto is located in the outer reaches of the solar system, far from the major planets, and Neptune is itself a gas giant with a strong gravitational field, the implications of such a collision would be significant. It would greatly impact our understanding of gravitational interactions and the evolution of the solar system. To understand the dynamics of a potential impact, one must first consider the structure and properties of the two planets. Pluto, despite being a dwarf planet, contains a variety of elements and compounds believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and it has an atmosphere composed mainly of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a giant gas planet, is composed mostly of hydrogen, helium, and other lighter elements, with a deep, dense atmosphere. A collision between such disparate bodies would dramatically affect their structure and behavior, potentially creating an event observable across vast distances. What makes this hypothetical collision particularly intriguing is the influence of other planets and bodies in the solar system. While Neptune's gravity plays a dominant role in keeping Pluto's orbit stable, it is not the only factor at play. Jupiter, the largest planet in the solar system, is another key factor. Jupiter's massive mass, strong gravitational field, and gravitational pull provide a stabilizing effect on Pluto's orbit, preventing it from straying too far into Neptune's domain. Moreover, Saturn's gravitational influence further complicates the dynamics of the outer solar system, making it unlikely that a catastrophic event will occur between Pluto and Neptune. Despite the apparent risks, ongoing research has also shown that the relationship between Pluto and Neptune is not as simple as a direct collision course. The gravitational resonance between the two planets, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3, creates a kind of cosmic lock that prevents them from coming into direct contact. This resonance is a key reason why Pluto and Neptune's orbits, while intersecting in the vast expanse of space, have never resulted in a collision. Their orbital mechanics are aligned so that the potential for conflict is minimized. To further understand the complexities of Pluto and Neptune's relationship, it is essential to consider how their orbits behave over long periods. Although Pluto's orbit crosses Neptune's, the two bodies never actually collide due to their gravitational resonance, which ensures they are safely locked in a stable configuration. This remarkable cosmic dance is a result of the two planets' orbital periods being in a 3:2 resonance. Essentially, for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This synchronization ensures that, despite their paths crossing in space, Pluto and Neptune are always far enough apart at any given point in their orbits to avoid a collision. This resonance is a beautiful example of how the delicate balance of forces within the solar system works to maintain stability. Without this kind of orbital harmony, Pluto would be at risk of drifting into a more chaotic path, potentially interacting with Neptune in a way that could disrupt the balance of the outer solar system. The gravitational interactions between planets, particularly those as massive as Neptune, Jupiter, and Saturn, also act as protective forces, keeping Pluto in a relatively safe orbit despite its unusual characteristics. In addition to the gravitational forces at play, the overall structure of the solar system also plays a role in minimizing the likelihood of catastrophic events. The outer planets, with their immense gravitational fields, act as sentinels, constantly shaping and reshaping the orbits of bodies like Pluto. This continuous interaction prevents the solar system from descending into chaos, with planets and smaller objects following predictable, though sometimes unconventional, paths. Despite these stabilizing forces, there remains an element of unpredictability in the long-term evolution of the solar system. As we continue to study the behavior of distant bodies like Pluto, we are reminded of how much we still have to learn about the dynamic, ever-changing nature of our universe. While a collision between Pluto and Neptune remains highly unlikely due to their orbital resonance and the gravitational influences of other planets, it still serves as a reminder of the complex and fascinating forces at play in our solar system. The possibility of such an event challenges our understanding and keeps us eager to explore the mysteries of space.